Hello dear aspirants, my name is Shravan Kumar and I am the faculty for Science and Technology. Welcome to Venkis Academy. In this video, we are going to discuss some basic concepts of orbits. There are different types of orbits in which the satellite revolve. So we are going to discuss some basic things about the orbits. Now let us first take this eccentricity. What is the eccentricity? Eccentricity is nothing but the deviation from the perfect circle. Usually, suppose if this is the Earth and if the satellites are revolving around the Earth, if the center of the orbit and the center of the Earth, if they coincides, we call it perfect circular orbit. But whenever there is a deviation from exact or perfect circle, then we call that there is an eccentricity for it. For example, if a satellite revolves around the Earth in elliptical orbit, it means it has eccentricity. Eccentricity E varies from 0 to 1. If the eccentricity is 0, it means perfect circular orbit. If the eccentricity increases from 0 to 1, then it means that it is deviating from the perfect circle. An ellipse has always two focal points. In fact, the Earth is also revolving around the Sun in elliptical orbit, where Sun is at one of the foci, and this is also the first law of Kepler, which governs the orbital motion. Now, second, coming to the orbital inclination. Inclination is the angle at which the orbital plane mates with the equatorial plane. Suppose if this is the Earth and this is the equatorial plane. Now, suppose the Earth, the satellite rotates around the Earth like this. This becomes the orbital plane, and this angle is the angle. This is the orbital inclination. So it is the angle which makes with the equatorial plane. Coming to the orbital period is a time that a satellite takes to revolve around the central object. Suppose if Earth is the central object and if a satellite is revolving around the Earth, the total time that it takes to complete one revolution around the Earth is called the orbital period. Next comes this retrograde motion. What is this retrograde motion? It is always called with reference to the motion of the central object. And again, I am taking the example of an Earth and a satellite. We all know that the Earth rotates from west to east. And similarly, if you take a satellite that rotates in the opposite direction, that is from east to west, then we call it retrograde motion. So once again, if you take an example of Earth and a satellite, as Earth rotates from west to east, and if the satellite revolves around the Earth in east to west, we call that motion as retrograde motion, since it is opposite to that of the rotation of the Earth. And similarly, the prograde motion is the orbital motion or rotational motion of a satellite with reference to the rotation of the central object. And again, when you take an example of Earth and a satellite, if a satellite revolves around the Sun in the same direction as the Earth rotates, that is from west to east, we call that motion as prograde motion. Coming to the apogee and perigee. See, apogee is the farthest point. So before I describe this apogee and perigee, there are two terms that similarly sound. One is aphelion, the other one is perihelion. Helio means sun. Aphelion means it is the farthest point of the earth in its orbit from the sun. That is called aphelion. That means the distance between the earth and sun is maximum at that point. And similarly, perihelion is the shortest distance between the earth and the sun in the orbit of the earth. That is called perihelion. And here it comes apogee and perigee. So here G represents GEE, this G represents earth. Apogee is the farthest distance from a satellite to that of the earth. And perigee is the shortest distance between the satellite and the earth. And coming to the next, Molniya orbit. This Molniya orbit is an orbit that has maximum inclination, and maximum eccentricity. The maximum eccentricity here is referred to 0.722. That is the maximum eccentricity we can observe. This Molniya orbit is usually, we take this orbit to cover the earth, maximum area of the earth. Usually, remote sensing satellites sometimes use this Molniya orbit. Next. Okay, now let us enhance our understanding through some pictures. So, this is the earth, and this is rotation, and this rotation is from west to east. And you see, this is the orbital plane. Along this red line, this is the orbital plane, and this is the equatorial plane. And this angle theta is the orbital inclination. This is the orbital inclination. So next, let us take the next one. This is about eccentricity. And you see this is perfect circle. So this is 0. This is perfect circle. When eccentricity is 0, it is a perfect circle. That means there is 0 deviation. But when we see the other orbits, it is completely deviating from the perfect circle. So as long as you see the deviation from the circular orbit, we say that orbit has some eccentricity. So this is E0, which represents perfect circular orbit. E is equal to 0.5, which means it is not a perfect circular orbit, and E is 0.75, it is very close to Molniya orbit. Next, so this is Molniya orbit. In this Molniya orbit, we can see that the eccentricity is 0.722, and that's why we can see, you can see this orbit is not a circular orbit. So this is an example of Molniya orbit, and these two pictures represent the motion, the rotational motion, the orbital motion of these satellites. The rotational motion, you see here, the rotational motion, the rotational motion of the satellite. This is the satellite, and this is from west to east. And if this is the earth, the earth rotation is also from west to east. Since both this orbital motion and the earth's rotational motion are same, we call it prograde orbit. And now if you see this one, the earth rotational motion is from west to east, but the satellite, it is going from east to west. They are not coinciding, they are not same, and that's the reason why we call it retrograde orbit. So prograde, retrograde. So next comes here, you see this is geostationary orbit. That means with reference to the orbital period of a satellite, it is exactly same that as the rotational speed of the earth. That means at the point, if you see at this point of time, if you see a satellite in the sky and that is constant every time, at every point, that means the rotational speed of the satellite and the rotational speed of the earth both are same. That is 23 hours, 56 minutes, 4 seconds. And the distance here between the earth surface and the geostationary satellite is exactly 35,786 kilometers. And this is constant. And this is standard. When the orbital plane coincides with the equatorial plane, it is geostationary satellite. But whenever there is an inclination, so this is the orbital plane, whenever there is an inclination, but still if the distance is 35,786 kilometers with some inclination, then we call it geosynchronous orbit. Geosynchronous orbit. The only difference between geostationary and geosynchronous is geosynchronous has some orbital inclination, but geostationary orbit has zero inclination. That is the only difference. The rest, everything is same. The distance between the Earth's surface and its orbit is 35,786 kilometers and approximately 36,000 kilometers. And beyond this orbit, we say that if a satellite is rotating beyond this orbit, we say that it is in high Earth orbit. That is the reason why we say that all geostationary satellites are geosynchronous, but geosynchronous are not geostationary. So next comes polar orbit. So if orbital plane is coinciding with the polar plane of the earth, then we can say that is a polar orbit. So next you see this, this is one classification based on the altitude. Altitude means height, based on the height. See, if this height is from the earth's surface, if the height is below 2,000 kilometers, we call it LEO. LEO satellites. LEO stands for Low Earth Orbit Satellites. LEO stands for Low Earth Orbit Satellites. And in this background, I want to remind you two things. One, the International Space Station, where we do several space experiments. And that station lies located in LEO, low Earth orbit, around 400 kilometers. And similarly, we did a mission, we organized a mission Shakti, ASAT, that is anti-satellite, we launched anti-satellite missile to show that India has the capability to strike satellites in the low Earth orbits. We demonstrated that in low Earth orbit only. So low Earth orbit, LEO stands for low Earth orbit, and it is up to 2,000 kilometers. And the next one is MEO. Based on altitude, we classify LEO, MEO, GEO and HEO. And this is LEO below 2,000 kilometers and this is MEO. From 2,000 kilometers to 35,786 kilometers. It is MEO. So 35,786 kilometers is geo orbit, that is geostationary orbit or geosynchronous orbit. And above, see, this is exactly, this geo is exactly at 35,786 kilometers, and above this it is called HEO. HEO stands for high earth orbit. High earth orbit. It is beyond 35,786 kilometers. And you see, this is GTO. GTO stands for geostationary transfer orbit. So in this, before it reaches geostationary orbit, it has to transfer into GTO first. So on multiple maneuvers of the satellites, we raise the orbit, 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 and then we reach 35,786 kilometers. And then once we achieve 35,786 kilometers, which is geostationary orbit, then we streamline it. And this is how the geo transfer orbit works. And coming to the Lagrange points. So Lagrange points are those points. Next. Now let's discuss the Lagrange points. So what is a Lagrange point? Lagrange points are nothing but parking spots between two celestial bodies. And these are stable points between two celestial bodies. So here the two celestial bodies are, one is the sun, the other one is the earth. And when a satellite or an observatory kept in this, at these Lagrange points 1, 2, 1, 2, 3, 4, 5, when we position satellites in at these Lagrange points, it consumes very less fuel. And Aditya L1, you know that Indian solar mission Aditya L1, it is placed exactly at L1. And this is due to the balancing out of the gravitational forces between the sun and the earth. And so we call them parking spots. So L1, it is in between sun and the moon. L1 is the first Lagrange point, and it looks like a rhombus. And it is the first Lagrange point between sun and the earth. The other one is L2. It is the other side of the earth. And again, the other side, if you see L1, L2 and L3, they are on single line. And coming to the L4 and L5, they are towards the right and left of the earth. So these L1, L2, L3, L4, L5, these 5 Lagrange points are nothing but parking spots or stable points between two celestial bodies. It is named after Joseph Lagrange, who is an Italian French mathematician. Thank you.